nanoHUB.org.
Online simulation, and more for nanotechnology.
So we're going to go ahead and get started. First of all, thank you everyone for joining us today for our webinar, Teaching and Learning with the MIT Atomic-Scale Modeling Toolkit's Classical and Quantum Atomic Modeling Applications. Our presenter today, Dr. Enrique Guerrero, has been a developer of the MIT Atomic-Scale Modeling Toolkit since 2021 and has an expertise in computational physics. And with that, I'm going to pass it over to Dr. Guerrero.
Thank you, Amy. So, I'm gonna take this kind of like a classroom. You can feel free to ask questions throughout, and I've talked with Amy, and we've decided she can find a good time for a pause, and we can go over questions as they go. So, don't feel shy and go ahead and write those down. My name is Enrique Guerrero. I'm a recent graduate, PhD grad from the University of California, Merced, with the Struba Ab Initio Laboratory, where we specialize in DFT and other quantum mechanical methods. This toolkit was created a while ago, like over a decade ago now, I think. But I have very recently been added to sort of revive it a little bit. And so this is the third and final part of a three-part series talking about this toolkit's capabilities. So if you're around, the first one was about a more broad sort of application and how is this useful. And my advisor, David Struba, went over the C.U.R.E method, our course undergraduate research experience. So if you were present for that, what you learned was that we sort of take this approach of appreciating the quantity, that there's many students, right, and that they can do research sort of to a much smaller degree than say a graduate student might in their entire research experience as a graduate student researcher, but still to a meaningful capacity, and they can do new research that's not been done before on say a new material, for example. In this example here, there's MOS2 molybdenum disulfide with a selenium dopant. As you see here, it's the lighter yellow one is selenium. And the idea is that the place where it takes over the sulfur spot can be is variable, right? And so if there's more than one selenium taking over the sulfur, you can quickly see that there's many possible combinations of where the selenium can be with respect to the sulfur. And so what students in this class did is they can look at, person A has one particular configuration and they can learn many things about it, and person B does to a different configuration. Something that, in theory you could automate, but the students learn a lot throughout this process. And it's valid sort of research data in the end, so it's good in that respect. The second talk was about the quantum espresso module specifically within the Atomic Scale Modeling Toolkit. So as you'll see today, there's several applications. If you were present to that, you probably were clicking around and seeing that there's other stuff going on. But I only talked about one module because that's the one that I've had devoted most of my time to updating. And that's the quantum espresso implementation, which is a density functional theory code, which uses a plane wave basis set. And in there, we practiced using it to compute some physical properties of silicon, such as the ideal, cell length or bond length, electronic band structure, density of states. However, we ran out of time for phonons. That was kind of planned, but now we have time for it again, and I know that interests people a lot. Since there's a lot of data, especially on Raman spectroscopy is one thing that everyone really likes because it's kind of like a fingerprint for your material. And go ahead and follow along to this website, nanohub.org/resources, UCB Comp Nano supporting docs. And make sure to download. So I'll go ahead and navigate myself. If you don't have an account, make sure to make one, an nanoHUB account. And make sure to download this document, the most recent one at the very bottom. They're the same, one's a PDF version. So I'll go ahead and open it. And the way I'm going to run this webinar here is I'm going to have the instructions on the right, just to give you an idea of what page we're on, or what part of the page we're on, and the simulation on the left. So let me open on the left. I've got my cheat sheet as well. If anything goes awry, I can just turn to it. But yeah, if you've made an account, you should be able to launch this tool and we can get started here. So the way this guide is written is a few sort of examples, going over the different applications in here, and you'll see pictures like this. Some of them might have markings, which you should pay attention to. That's where you should be focusing. And there's also some regions that are highlighted in green. That means that you need to input something. You need to input what's here in order for the code to understand what you're doing. And the very beginning, I do have an introduction, just a one-liner as to what each of these things do. We're not going to go through all of them. That maybe was my original very ambitious plan. But instead, I've sort of selected a few of them which sort of give you a good sense for what kinds of things are in here. And if we have time, then we can go over this list and you can see what other stuff there is. Just to give you a very brief overview, there's one application which is just about basic statistics on a data set. There's a few that are molecular dynamics. They used LAMMPS, LAMMPS. I think it's Sandia that writes that code, which is molecular dynamics code. There's a few Monte Carlo sort of in-house, I believe. Games is a quantum chemistry one, which is probably beyond the scope of this lecture a little bit. And then there's two DFT codes, density functional theory, one of which I covered extensively last time. And yeah, if you didn't attend that one, I would recommend on this website downloading this guide if you want to try and go in detail if you're really interested in doing the DFT portion. Okay, so on to our simulations. So yeah, as you saw, this toolkit here has several applications. They're navigated through by this guy here. There's a few sort of UI things to keep in mind. The one sort of thing that you might need is terminate. That really sort of ends the session. You can have 3 sessions running at a time. So if you want, you could do a second tab and do this twice for whatever reason. Say you want 2 different sets of parameters, though there might not be a need for that, as you'll see. But you might need to hit it also if your thing crashes, it's not responsive, etc. If you don't want to terminate your session, you can save it for later, or just close out of the window and you can come back next week and you can open up right where you left off. But it's probably good practice to terminate if you're not going to come back to it. Refresh sometimes also helps when it gets in a jam. And also there's this resizing tool to resize the window. It sometimes helps with seeing where the scroll bars are. Okay, so the first one that we're going to do here is the molecular dynamics Lennard-Jones. And if you're learning MD or simulations in general, this is probably one of the first few chapters in your book. It's perhaps the simplest potential that still gives meaningful results. And it says follows, 4 epsilon times sigma over r to the 12th minus sigma over r to the 6th. Okay, r is the distance between two bodies, two particles. Sigma is just the size of the well of a potential, the depth of this well here, and sigma is a sort of particle size, and it tells you, yeah. So if you didn't see it before, well, if you saw the left screen, then you saw it. I was just mentioning that there's markings all over this document. Yeah. So just starting over here, this is the equation for the Lennard-Jones potential. 4 sigma times and then sorry 4 epsilon times sigma over r to the 12th minus sigma over r to the 6th, and this gives you this shape where the depth is epsilon and sigma is something about the size of the particle, and how much they collide. And we sort of know that, say, two chargeless particles behave this way. If they get very, very close, there's a Pauli repulsion. They don't like to be so close, and so there's a very strong repulsion near zero. But if they're very far away, there's no interaction whatsoever, and so this reaches zero. And there's only a few parameters to worry about on the left here on our simulation. And I've highlighted what we should change for our first little Lennard-Jonesium, I think some people call it. It's just like a sort of fictitious material. First, I want you, if you're following along, to go ahead and increase the number of particles to 64. And we're going to change the box size to 3.5. And then the number of simulation steps to 10,000. Okay, so what did we just do? Well, we're going to make a little model with our particles. I chose 64 here. It just gives a better visual, as we're going to be able to see the actual system, as I found playing around with it. There's a temperature here, which sort of gives our particles a little bit of a kick initially. And it's random and, well, pseudo-random. And you sort of can intuit what happens. If the temperature goes up, the particles start going crazy. If the temperature goes down, they're very still and immobile. Box size has to be tailored to how many atoms we have. If it's very small, it's a very dense material, but if it's too small, we start reaching computational errors. Yeah, so again, the document on the right, you guys should have access to it. So yeah, I'll go ahead and zoom in on the left to see these a little bit better. Yeah, so the box size, and it says in units of sigma, will really decide our density, is how you would see it in literature, not really so much as the size of the system. Yeah, and if you notice there, when I moused over this box, and we saw a little explanation. There you go, an explanation for what the variable is that we're inputting. So that's one source of information. Okay, potential cutoff is a bit of a cheat. Okay, so as we saw on the right, the potential drops to 0 when they're very far, and so all that we are doing here is we're saying, you know what? If any particles are beyond 2 sigma, then let's just ignore them. Let's just set it to 0. It saves a little bit of computation. The time step, so this is going to be a Verlet algorithm, but don't worry too much about that. If you imagine that there's many particles and they've all have some sort of velocity, a time step is essentially how much they're moving. And if it's very small, it's going to take a lot longer to calculate, but it's going to be more accurate for a longer time. Number of simulations, inversely, this is how long we want to run it for. Do we want it to run for a few femtoseconds, relative, or 10 times that, 100 times that. This combination of parameters is one that I found works pretty well for what we're doing here. And so we're ready to go ahead and simulate. And so on the top right, go ahead and click the simulate if you haven't already. And it will do a little bit of thinking. It's not a very long code, or sorry, it shouldn't take a long time. As you can see, the potential is super simple, and it's only acts on 2 particles at a time, as simple as it can get. Okay. And now we got a nice little movie to go along with the description I just gave you. Great. Yeah, so keep this picture in your mind, and maybe think about, what kind of a material would this be? It's not real, right? It's fictitious, but does this look like a solid, a liquid, or a gas? Okay. And so now we click back on these tabs here. If we close it, we won't get it back. We'd have to resimulate it, so don't close it unless you're ready to. There's all sorts of options for the viewer here, but nothing we need to worry about right now. We can go back, and what I want to focus on are these results files. So a lot of these applications, by the way, work in this sort of same scheme. So you sort of learn one, and then the rest become easier to understand. So all of these are files, okay, that were generated by running this code. Some of these are obvious. Final XYZ coordinates. Well, that's at the very last time step. Where are all the atoms? And this might be useful if you're trying to, say, export the data and put it somewhere else in your own sort of code here. The LAMMPS file, this one's really interesting because this is the output from LAMMPS. But notice that there's a lot of keywords here and some values. And so if you're the sort of person that likes to troubleshoot, if you really want to make this work and you keep maybe running into errors and you don't want to email someone, this is a good place for you to go and say, you can Google, when I do it right now, I'm not afraid of a live Google. Let's do LAMMPS, and then say I don't know what velocity all create means. Velocity all create, and yeah, we should reach the LAMMPS documentation, and it tells you exactly what that means, and then you can find out from here if you're used to reading documentation, what the 1 and the 17 mean. Yeah, so yeah, this is a good page especially if you're running into errors. I will say though, it's not hard to break this, but it's also very easy to fix. If you get an error, it's very likely that your system is just too dense. Or perhaps too sparse, but more likely it's too dense, and maybe you need to make it a little less dense, put the time step down as well. Okay, then we got a few sort of variables. We don't really have too much time to look through all of them. There's a few that I thought were important. One is the autocorrelation function. And so this is like a sort of time-lagged image. It's the correlation between the system and a time-lagged image. And the point is, if there's a strong correlation, then this value will be 1. If there's not a strong correlation, that value will be 0. And what that means is at 1, the system sort of resembles what it used to look like. And at 0, the system does not really resemble what it used to look like. And that's good in this kind of simulation. Typically, we want to get to a sort of equilibration, okay? And that you'll read that same stuff here in the document if you follow along. Is we sort of want this kind of value to reach 0. That's a symbol of us having reached some sort of equilibration away from any sort of hysteresis or memory from our initial state. There's also this radial distribution function, and what this function is it's sort of the relative probability of where the atoms should be. So what I mean by that is, suppose you have two atoms, and if they're 0.5 away, this plot is telling me that there's like a 0% chance that they're that close, and they really should not be with this potential. There's a very high likelihood, or a relatively high likelihood, that they're at this distance, which, if you remember, it should be 2 to the 1/6 sigma. And further away, there's still some shape, some medium distance where it's less likely. 1 means a value of 1 is the same as if you had a particle and there's particles distributed all over space randomly, completely randomly, with no sort of correlation, no interaction between them, then you should get a value of 1 for this. Okay. So with that in mind, what we can do, and this is where this system starts to shine a little bit, is we're going to redo the computation, but we're going to increase the box size, not to 45, 4.5, okay? And we're going to hit simulate. Yep, and we're here. And then we're going to repeat that for 5.5 and 6.5. And the point is, we're going to have a few densities, and it's remembering what we just did. So here's the second animation. It's going to just go, so for example, if we go back to this radial distribution function, you notice now that you have a slider, it goes from the first simulation to the second simulation. So let's go ahead and do 5.5 and 6.5 a little bit faster, and then we'll look at those values again. See how we're doing on time. 35 minutes. Okay. Yeah, are there any questions at this point?
Someone did ask, what are we doing? I think they mean maybe right now what you're putting in.
What am I doing? So I'm increasing the box size from 3.5 to 4.5 and 5.5. So we're on this section, the first section, step 9. Okay, so we've looked at the files. I talked about it being equilibrated. We talked about the radial distribution function. Yeah, so we're chugging along here, even though it doesn't feel like it. Yeah, and so here's the last one, the 6.5 one, and as you can see, it looks way different from our first one, right? So this is our first guy, and this to me resembles more of a liquid, maybe some high temperature solid, but this one is it's sort of more gaseous, and it's quite sparse, and we could go much more sparse, of course, but in the interest of time, yeah, I'll just show you these plots here. This is the radial distribution function, and you can see as we increase it, a few things happen. Well, first of all, notice that beyond the first 4.5, this peak occurs right here, but at 3.5, it actually occurred below some value. So they were compressed at 3.5 box size. But also at very high values, it flattens out and we lose a lot of correlation, as you would expect from a gas. Okay, so that's the Lennard-Jones. What variables are considered? Yeah, so
yeah, it looks like 2 came in. That first one mentioned which variables are considered for this calculation.
Yeah, so maybe your question is, how do these variables sort of relate to the formula? Right, so this formula here is only about 2 particles, right? Whereas these variables are about the entire system as a whole. So what we're doing is we're setting up the box, the bounding box with particles inside of it. And here, let me just draw one real quick. This box, we're making it bigger and bigger. That allows the particles to move further and further away from each other. And so when they are farther, this value of R is what's changing. This R is the it's like the x-axis. It's what's the input, right? This epsilon and sigma are constants. Um, okay, so I also saw a question about this second neighbor. Yes, yeah. So this potential here is only about two particles, whereas the setup here sets up where all the particles are. Okay, I saw a question about G of R, and about extra neighbors. Say maybe in this one it looks like there's more information here. So this is a sort of quirk of periodicity. So these boxes are periodic, and when they are periodic, a G of R doesn't really function in any physical way uh, beyond half the box size. So notice this is at 1.75, which is half of 3.5. Um, it exists, but it's not realistic. You get into like weird. So just imagine the sort of a box and a circle inscribed beyond it. Because it's box shaped and not spherical shaped, there's some weird things that happen at the corners. And so G of R doesn't mean anything beyond it. So in order to get the same density and to see more of these peaks, as that person correctly mentioned, we would need more particles and a bigger box. But we don't have time for that. Yeah. Yeah, thank you for your questions. They're very helpful for everyone here. And all right, let's keep it moving here. So now that we've come back and we've revisited these, if there was time, we could say take some of the data out and put it into our averages and error bars guy, but I don't think we will have time, so let's move on to carbon nanostructures. Okay, so this module here also uses LAMMPS as well, but it's a little bit uses a potential that's more sophisticated than the Lennard-Jones. It's one of these options, and if you don't know what they are, you can always look them up in LAMMPS. Sufficient to say that the Tirsoff is a very standard one at this level. And what I want to do now is I want to look at a carbon nanotube, but more specifically, I want you all to think about a classroom and how this might work with many students in a class. Okay, so keep that in the back of your head as we go through this. So let's turn on compute stress. And what we're going to do is we're actually going to compute the 6,6 carbon nanotube. This particular application here was built with many different carbon systems in mind: graphene, fullerene, and CNT with various, asterisks, pretty much. But you can also upload your own if you are, interested in nanotubes. There's actually a website here, TubeGen, where we can generate your own tube coordinates, and you should be able to just upload them directly here. So let's go ahead and run it as is, just this base CNT example that's here. Let's simulate. And what we're doing is actually just minimizing the atomic coordinates. We're allowing the atoms to sort of move in a way that minimizes that Tirsoff potential. I'm not sure if you can calculate the stone wave effect. Surely you can with LAMMPS, LAMMPS on its own. But this particular application is probably too simplistic to do something like that. So yeah, so if you can see here, let me move this a little bit. We have just a regular old tube with, I don't know, some 50 or so atoms, 60. And this is a nice picture, but what we actually care about, is the science. So let's go ahead and go back to this tab. And you can look through here at the energy. And here's where you can, see what's happened throughout this minimization. Throughout the steps, throughout this process. the energy has gone down, and that's a good sign that we are minimizing the energy, right? Um, there's a few other things to look at here, but mainly they're all coordinates. Again, here's that radial distribution function. But within LAMMPS, if you look at the LAMMPS log file, you can find that because we turn the stress on, we should see this section which shows PXX, PYY, and so on. Yeah, so here we'll have the pressures or stresses. It's a tensor, and here's the 6 components of it. A 3 by 3 tensor, the 6 non-degenerate components. So why I want to show this to you, even though we're not going to calculate it today, is because we can extract from here the sort of Z stress, we can input strain, and we can from that get the sort of Hooke's relationship. That is a stress equals strain. Well, stress equals the elastic tensor times strain. And that's what gets you to quantities like the Young's modulus. And this is where I think students can sort of shine. They each get their own material, and they can say calculate the elastic modulus. That's the kind of thing that we have done in our class. So yeah, what we're gonna do is we're gonna introduce a defect. Okay, so and it's really simple here. All that I said to do here is to remove an atom, right? So let's go ahead and put this down to 383 atoms and remove any random atom, okay? I know many of you are probably going to choose the first one, which is fine. I might choose something in the middle just to make it a little bit easier to see, but also after we hit simulate here, also, the idea is that we actually have different atoms removed. Every student would have a different pair of atoms removed. Okay, so if I say look around, maybe I can find. Let's see if I can find my defect. Oh, I don't see it, so let me go to the easy one, and just go ahead and remove the first one. Create it too. We'll do that for now. Yeah, so this one is on the edge. Can I twist my CNT? Yeah, so if you saw that there was a few options available, right? But if you want to, get your own chirality, I would recommend you hit this website up, TubeGen, and it's in the document, the link to this website. And messing with these chirality indices is how you can change how many twists your CNT has. Oh, and there I see the defect. About since I picked the first atom, it's at the very edge, right here, right there. Okay, and the system minimized in energy, and so this bond here you can see sort of moved away. And I know it looks like this is just the edge of a CNT, but it's periodic, so that means this end is touching that end. And we can see that the energy, so I just did 2 different computations. The energy signature here is different. I can once again scroll between them. Simulation 1, 2, and 3. As you can see, they're increasing in energy. It doesn't like having a dopant in the system. And what we can do is if I put 2 dopants in the system, I didn't find where the other one was, but I can tell you it was not a divacancy. If we reset this back to normal and then say delete 2 atoms at a time that are right next to each other and simulate, now we have something to compare against. We have 2 systems which have two defects, but the two defects are at different locations. Okay, so notice here, it's got a big chunk like someone took a bite out of it right here, and that's divacancy. Two atoms are missing. And if we look at the energy, and if we compare our last two simulations, so this is 3 and 4, it turns out that the most recent one I did is lower in energy. That means a divacancy in this case is more stable than having two single vacancies far away from each other. But how far? What if it's just one atom away, or three atoms away, or across the entire CNT, right? This is where you can get more students involved, and they can each have their own sort of, pair of vacancies. They can maybe compute properties about them. Maybe they can do DFT on them, and find the band structure or something. This is where I think a tool like this is very helpful for this kind of activity. Let me get back to my page here. Somebody asked about combining two different CNTs. It's sort of up to you at that point. You're on your own in a sense. Like you'll have to figure out what the atomic coordinates are that make that periodic, and you would have to minimize them to get to a reasonable structure. Because the only stuff that's implemented is this few sort of pedagogical materials. But yeah, that's a good question. Okay. Graphene oxide. Yeah, so before we move on, sure, let me see what that looks like. So we have in this, let me move this up. We do have as options graphene. I'm not sure if by graphene oxide you mean just one sort of oxygen defect, in which case the answer is yes. You can just, put an O there instead of a G. Or if you mean some sort of a structure, then you would need to input what that structure is, and you'd need to find it from somewhere else, or yeah. Is this software better than quantum ATK? Well, quantum ATK has the word quantum in it, and so that means it's a quantum computation, right? And so this one here is classical, and so definitely not better than that in that sense. I believe quantum ATK is also a little sweet. Let me see. Polymer modeler. Yeah, so I will sort of say that there's a lot of stuff. I think every time we look at these things, there's a lot of stuff that you want to do immediately, especially when you see something like carbon nanotubes. And you could do all these things, but the way that we built this was more about teaching, about students learning how do you simulate, how do you model materials, and what are some of the more basic stuff. For example, the Ising model is in here, right? So I wouldn't really trust any real science, any sort of like, I'm going to go out and invest in building a new material based on the Ising model. It's just not that robust a model, but it's a very good teaching tool, right? And so that newest question that we got there is more on the line of what I'm thinking when we see this this tool is, what are the phase transitions? That's a good question. So what we can do, for example, in the Lennard-Jones ones that we looked at earlier, is we can try a bunch of different temperatures, a bunch of different box sizes, cutoffs, and we could see where the system might behave differently. And I was going to come back to this later, but since it was asked, you can see that there's a high pressure in the first Lennard-Jones simulation, and low pressure in the other simulations here. And that's a sign of a phase transition. And so, yeah, that's one thing that we can sort of learn about.
Okay, I also see, can we perform publishable calculation by uploading our own structure?
Um, Not likely unless it's very small. I wouldn't recommend it. So you'd be using nanoHUBs sort of resources to do computation. Perhaps if you have a very small system, some of these quantum Monte Carlo ones, it would be sort of like exploratory in a sense. But like I had said earlier, the Ising model, not something you really can publish on unless you have a completely new insight on the Ising model. The next one I want to talk about here is the quantum espresso one. Um, and we talked about it last time in great detail, but there was one thing that was sort of absent, and that was phonons. And so I really wanted to get to it if anyone's interested in, for example, Raman spectroscopy. So yeah, we'll see here that you can get publishable results, but on this system, it would take, hours, whereas if you had access to, you know, even a sort of simple, modest supercomputer with just a few laptops hooked together, you might get much faster results. Um,
We
yeah,
did have
so
another question come
okay.
in. Since this tool is periodic, is it able to calculate different values with varying chirality, for example, to see differences between metallic and semiconducting tubes?
Um, yeah, so uh, it, don't be too afraid when you hear periodicity because of can it capture some things where periodic is sort of not what you want. You can always cheat your way through it. Whenever you have a periodic system, like we did in this carbon nanotube here, and let me draw the box real quick. This isn't actually the periodic box, but let's pretend it is. What you can do is you can just increase the size of your box big enough such that neighboring nanotubes aren't close enough to interact. And so yeah, you should still be able to reach some situations like that. Graphene nanoribbon. Um, I suppose if you know how to cap the edge of the ribbon, you can start with this graphene here, and again increase the box size until there's a big gap, and then cut off a lot of your atoms. Should be possible, but might take a while. If yeah. Okay. Okay, so yeah, let's move on to the espresso one. What uh, I want to sort of remind you or tell you if you weren't here before, um, the way that the paradigm behind this system here is that there's two main tabs. One is the physical system, and the second one is the calculation parameters. They're sort of about the approximations that we then take into espresso, which does plane wave density functional theory. Okay, if you don't know what that is, so it's quantum it's a quantum level theory, so it's more accurate than what we were looking at earlier, but of course it takes a lot longer. And there's more to be said. I recommend checking out the previous tutorial. Um, so what we're going to change here is the system. We're actually going to try and do MOS2 single layer. And in order to do that, you just need to follow these values here. So we set it to arbitrary full lattice vectors. We're going to put in 1, 0, 0, negative 0.5, 0.866, 0, 0, 0, 3.890. Okay, so if you didn't catch that, it's of course in the zoom in again. Yeah, right. It's of course in the document on the left, on the right. Excuse me. And let me make it a little bit more legible. Yeah. This is just the hexagonal cell, and we're gonna set this value to 3.19, and we're about to do MOS2, molybdenum disulfide. Okay, and if you don't know what that is, you'll see what it looks like in a second here. It's just it's a semiconductor. It's really quite special. It's a 2D material. So I'm going to put in it's in crystal coordinates. There's a molybdenum atom at 2/3, 1/3, and then halfway up the cell. And there's two sulfur atoms. One is, and they're both at 1/3, 2/3, but they have different z coordinates. And again, I don't recommend following this from my screen. Instead, try doing it from the document. Or if this maybe don't get lost at this point, like just don't do the calculation if in this part if it's a little too fast. That was the physical system. That's the MOS2. The next part is all about our approximations. And if you know about these approximations, you know that what I'm about to type is practically heresy. They're very, very weak approximations. However, we don't have the time. Even just modest approximations might take 7 minutes, which is perhaps too long. But I did do one, and it's saved here, and it took 25 minutes. But for now, let's go ahead and simulate just this. Well, actually, one more step, sorry, is the phonons. Of course, the thing we're interested in is let's compute the phonons. So I said that these first two tabs were basic and required for all the computations. These last four decide what are we going to do with our system now, okay? And so what we're going to do is compute the phonons. We want to turn, if you follow these instructions here, turn this on, calculate Q equals 0, turn Raman on, and visualize an X-Kristen on, okay? And now we're going to simulate, and this should take less than a minute. Okay. And are there any other questions? Any recent questions, maybe? As this is simulating?
One question, is this useful to manipulate perovskite? I don't know if I'm saying that right.
Perovskites.
Perovskite.
Yeah, so it's all whatever you put into it is what you're going to get out, right? So in Quantum Espresso, this interface here, it can really let you do a lot. Not like there's, say, maybe 100 variables that we don't use in this interface here, right? From Quantum Espresso, which is, robust and can handle anything you throw at it. It just might not be correct if you throw at it something that's pretty crazy. But of course, perovskites have been done. We do them in our group, and you could do perovskites with this. You could even do Raman with perovskites. But the number of atoms might mean that it will take a very long time to do a phonon computation. As you can see, we have 3 atoms, and I put very weak approximations, and still it's taking about a minute or so. So you can imagine the scales as n to the 4th. If we increase our atoms just a little bit, then it gets a little bit wild and unwieldy. Okay, so here now we have these two new tabs. One is X-Kristen, shows us a picture. The other is an animation slider. So if we press F, the letter F as in Fox, or if you go to display and click forces, here forces, you should see arrows that indicate the direction of movement of the atoms, the atomic displacement for the different modes, okay? And if we go here, we can slide between the modes. So that was mode 1, this is mode 2. Okay, and if you know about phonons, then you'll recognize that these are all going in the same direction, and that means that these are the acoustic modes, the 3 acoustic modes. But then further, we get more interesting directions. Okay. How do we see the results? Tab with figures. If you're on this simulation, perhaps it's not done yet, but these should pop up in a second once it's done. But if you go back here, then we see the results, the sort of log of results files. And the one that I want you to notice is this Raman spectra one. Can you include spintronic? I don't remember. I don't recall if we've it did. I think actually yes that we have spin resolved like LSDA. Um, so yeah, you should be able to do that. Yeah, go ahead and click on the Raman spectrum, and we do have a Raman spectrum. It's not a very good one, admittedly, because of our bad approximations, but um, it's it's something. Even for something so weak, we got something that's not really that far from reality. If you look at the documentation here, this is an experimental Raman spectra of MOS2, single layer. And this is my computation of bulk MOS2 that was published, so it's published worthy. I used ESPRESSO. I didn't use this interface, but I did use ESPRESSO. And you can see that there's two peaks. We don't have two peaks. We only have one, but it exists at 396, which is, around about in between these two. And so I think what happened is it sort of merged the two peaks together. Which, if you know, again, if you know what I put into the input, that it was quite a wild approximation, then that's actually really quite good that we got this peak. Let me show you the one that took 20 minutes. That would be this one, and we get, and I put more atoms into it. There's all these interesting modes. And we get the Raman spectra with the nice two peaks, a bit of other stuff. Again, a bit of other stuff happening, but we do have these two main peaks. Yeah, so that's how you can do a phonon computation. But I would definitely warn you to start small before going big. So looks like we have about 5 minutes, or a little bit less. We got a lot of good questions, and so I definitely prefer doing questions than just sitting here and talking. But of course, that does mean that it eats into our time. The last one I wanted to show was this Ising model, and so I'll just sort of show it to you, and you can get a sense for what's happening here. What the document here tells you to do is to change the parameters by clicking this tab here. So I see same question as Deepak. So could you repeat that question, Amy, maybe?
They asked phonon band structure.
Oh yes, phonon band structure. That's implemented, yes. But you need more Q points. So it takes a long time as well. But yes, that's implemented. You can do. If you want to see what that's like, just hop back on this real quick. In the input, in the Phonons tab, you would turn this off. We need some sort of Q grid, say a 2 by 2 by 2. And you say, yes, I want to compute the phonon band structure. And there's various ways to input it. If you follow the ESPRESSO documentation, the guide to the ESPRESSO one from last time. It should be in the same file. Yeah, so back to this Ising model. Let's go ahead and just start this or set these parameters. Okay. Yeah, you're welcome. So I just changed a few things about the size. That's it. And so it's bigger now. And the way that this one works, it's sort of it runs the Ising model over time. I can start it and stop it with this button here. You see it says start. So if I start it, it's reached a state and it sort of stops there. There's nowhere else to go. And the temperature I set was 0. So it just froze and we get these nice big regions. And so if you come back and maybe increase the temperature, do something interesting like that, set those parameters, and then we start. Then we get, different activity. And back to that question about phase transitions, you can do the same kind of analysis here where we vary the temperature. And in fact, there's a sort of way to automatically vary the temperature here. Um, and yeah, so we can I just reset it, and then we can see that it anneals. Um, yeah, so this one is really quite handy. I think this is probably my favorite one. If we, for example, change some of these other options instead of dots, uh, let's see, constraint to z-axis, xy plane. We see arrows that signify the direction of spin, and yeah, if you follow the documentation, you can sort of understand this if you don't already know what the Ising model is. The idea here is that neighboring arrows, they either like to be aligned or they like to be anti-aligned. And there's an external field that we can put in. Um, uh, and that will sort of influence the direction of which way these align. And then there's temperature to sort of mess things up and jumble everything up. So yeah, go ahead and give this a try if you're interested. Thank you all for listening. Actually, I'll keep taking on any questions. Is this software integrated with Python? Well, it's funny that you mentioned that. I think a few of these, definitely this one, and I believe this one too. They're written in Python, but you can't say call this toolkit with Python. But some of these are written in Python, some of them are written in Perl. Um, yeah. Oh, thank you for your comment. Yeah, I think if you always keep in mind how could this be used for students, um, how could they learn? You don't have to teach students anymore. Like you don't have to teach them how to use Linux, how to use Bash, which is what I would have had to learn in order to use Quantum Espresso. Um, and so yeah, um, I think this tool really sort of it can be a little bridge or maybe a sort of crutch for those kinds of students. Okay, and so Tanya's mentioning that there's some sort of interface between Jupyter Notebooks and Rapture. That's really cool, and I'd really like to see that because I didn't know about that. Everything here should be free to use. Some of these codes. Oh, trial. Okay, I understand now. Yeah, you can use this code to your heart's content, or this system here. Uh, all the stuff here, Espresso, LAMMPS, and Siesta as well. They're open source. I don't know if they're open source, but they're free software you can download and use. I believe they're all open source as well. But yeah, so everything here is free.
Thank you so much, Dr. Guerrero, for this wonderful presentation. Thank you, everyone, for joining us today. We really appreciate it.